Okay, let's look at example 4 in the book. That one's got horizontal rectangles. So it says find the volume of the solid. Find the volume of the solid formed by revolving the region bounded by the graphs of, so we've got y equals x squared plus 1, a nice parabola. Y equals 0, is that a horizontal or vertical line? Horizontal, and x equals 0 and x equals 1, those are vertical lines. So we need to draw that region first, and then it says revolve it about the y-axis. How about we revolve it about the y-axis, then let's pick some other axis.
Can we revolve it around the y and then like around like x equals 5 or something?
Sure, yeah. Let's just pick one. I mean, you can revolve around anything, right? I mean, you can even revolve around. So I was just thinking, can you revolve things around a diagonal line?
No.
Oh yeah, I'm sure you could. I bet the computations would be much harder. I bet that'd be. No, I don't know if that's not a standard. There's no reason to do that. Think about why you're doing these revolutions in the first place. This is kind of like basic mathematical modeling, and lots of the shapes we're doing have real life shapes to them that model things like pieces of jets. Like, think about some of these shapes. Like this one, I think, could be like a jet intake engine, jet engine intake, something like that. These are designed to model things that actually are out there. That's why they're there, because sometimes people need to find the volume of their jet engine, or they need to find the area on the surface of the jet, of a flap on the jet. You know what I mean? That's just my example. It popped into my head. Why'd that example pop into my head, you guys think?
Because the shape looks like it.
Yeah, because the shape looks like it, number one.
You wish that you had a jet.
There we go. Actually, because I've studied things where the solids of revolution were used in the context of jet engines. So I know they're used there.
I want a jet like out of G.I. Joe.
Those would be
so I can just land here at school and then fly home and fly back and much faster.
They have those Harriers are like that, right? The old ones. And the new jet,
the Ospreys, those are cool. Like the
British Harriers. The U.S. has developed an F something to replace that. It's really expensive though, so they're not producing it too much right now because we don't want to spend the money. But it does do that.
No money.
It does that, just like the G.I. Joe thing. Okay, let's draw this before we get on too much of a tangent.
We could draw a tangent line.
Yes, calculus puns are the best.
Focus.
Okay, where do I draw? Help me.
Not really.
I need help.
Up one
X
parabola.
squared.
I think you guys mean this. Okay.
Yeah.
Y equals 0 is here, right? Maybe I should dash that line to see that we know what we're talking about. Write it down. X equals 0 is this axis. X equals 1 is like right here, right?
So that area is that little.
Yeah. So can we see the area that's bounded? This little guy right here. I don't know how high up that goes, but it goes up some. Let's see. Yeah. Okay, so first I want to, from our first problem, we'll call this part A. Let's revolve and find the volume by revolving around the y-axis. This is the y-axis, right?
So it's 0.
So, if I want to revolve around the y-axis, am I using vertical or horizontal rectangles?
Horizontal, so you go 0 to 2. Right, that would be your limits of integration.
How'd you know 2, Austin?
Well, you would calculate the intersection, I guess, but
So Austin,
I just looked. It says it.
how do you get 2 for that intersection? That's where x
You can
equals
set
1.
them equal to each other, I guess.
Which ones? X equals
Why don't you
1
just
and...
plug 1 into the y right
When you
up
set
there?
those equal, though, it's kind of like plugging 1 in, isn't it?
Just plug it in.
Yeah. It's kind of like plugging 1 into that, isn't it? Think of it like that. This is the point 1, 2. Okay. So Austin's saying, well, that means our rectangles go from y equals 0 to little teeny rectangles up here at y equals 2. Yeah? So our integral goes from 0 to 2. This dimension is dy, right? Remember, use the hints the calculus notation provides you. dy means these must be y values, right? And then we've got to do, this is a disk, right? So the disks are going to become like this. So our solid kind of looks like it's got like a dip in it. It's kind of like a bowl, isn't it?
So it's
Yeah. But each disk is a circle,
pi r squared.
so pi r squared.
Pull your pi off.
The only question is, what is the radius? This
So
part.
won't that big radius just be 1, and then the little radius is x squared plus 1?
There's no little radius.
Oh yeah, it's a disk. Okay, sorry.
Radius is 1. It's just you have to like subtract out the area between y equals 2 and y equals x squared plus 1. If that makes any sense.
Kind of. You guys know what she's saying?
It
Look at the
one
picture in the book. The
minus-
picture on example 4 kind of shows you the kind of shape that you'd get. I think it does help. You guys see it? Let's see. Put it on the camera here. So
They
Solve for
separate
y
the
first.
interval.
That's what you have to do.
do you guys see what they did in the book?
They separated the interval.
The issue is when you have these, that's really simple, isn't it?
Yeah.
But once you get to your rectangles that are up here, it kind of changes. So instead of just doing one integral, I've kind of got to split this up. Where do I have to split it up? Where's the
That
change?
one.
It's like right there, right? So otherwise, I think we'd either get too much or too little area. Does that make sense?
So 0 to 1 and then 1 to 2.
From 0 to 1, I think it's pretty simple, right? 0 to 1, what's the radius?
1.
Radius is just 1, so we go pi 1 squared. But then, when we're going from 1 to 2, in this region right here about, you can see that you don't want all this, right, for your volume. That's like the hole in the cup or whatever. So how can we do that?
And you have
It's
the
going to have to be like the
radius
washer
of
method,
a
isn't
It's
it?
going to be like the washer method
You're gonna
at
do
that
the
point. So we've
R.
got like, I'm going to pull my pi out in front. We okay with that? We've got big R squared minus
That'll be the
little r squared, still dy. So we've got, this one is going to be
pi.
0 to 1 pi dy. That's easy. And over here we've got 1 to 2. Except what's big R?
Isn't little r x squared plus 1?
Big R is
Big
1.
R is the
Something like that,
square
yeah.
root of 1 minus.
Big R, what is big R right here? Big R is this, isn't it?
One.
It's just 1.
Okay.
Little r is square root of y minus 1 squared.
Okay, so notice this is dy, right? So should you be putting x's in here at all? You shouldn't. That's a big clue to you. I sometimes forget about that, but see, the notation is there to safety net you. It's there because it needs to be, but it's also there to help you. So this is, it's on this curve, right? I need another color again, and I keep forgetting to bring one. But what we want to subtract out, the little r, is this dimension. You guys okay with that? That's the little r I want to subtract out. And that distance is the x value on this curve. So the x value on this curve is what I need to solve for and
Y
express in
minus
terms
y.
of y. So you go y minus 1
Root.
equals x squared, so that means x equals plus or minus the square root of y minus 1. Now that plus or minus,
You just need the positive because of the side you're looking at.
I think that we just want the positive. Are we sure about that?
Negative would be on the left.
Because it's just the radius, and so your plus or minus gives you both sides, but because you want
I
just
think
the
the
radius.
positive one, if you do it this way, you're going to get this positive
Yeah.
x value, aren't you? If you put a negative in front of this, it's just going to give you this value over here and make it negative and reflect it. So I think we want the positive
But since
value.
it's a radius, is it ever negative, really?
Yes, and it's a range, but if you
Yeah.
wanted this dimension on your setup up here, that would be the negative root.
But you're
We
squaring
want
it
this.
You want the
either
positive.
way.
Yeah, I mean, it's not, you don't have to
Yeah.
get into that too much. But, so we're going to put that there. So it's the square root of y minus 1. Now we're good because we have y's in both parts,
And that's squared.
but that is squared. So it's going to become pretty easy to integrate, right?
That's just going to be y.
work
'cause
it
it's
out.
one.
Finish that integral. Yeah, should be pretty easy. replace these two y's with a 2y. Got a 1 from here. That's really just 2. So 4 minus 2 is positive 2. And over here I've really got 2 minus a half is 3 halves, but that's minus 3 halves. So I've got pi times 3 minus 3 halves, which is 6 halves minus 3 halves, which is 3 halves. However you did your algebra, I think that's the answer. Is that what they got? Let's see. Calc. Is that what you got?
Yes, I got 3 pi over 2.
And units?
Units cubed.
Units cubed. Let's remember, if we drew this, this solid would look like this, except it's been spun this way. So it's a solid that's been spun this way. How far out at us is it going to come? 1 unit, right? It's going to come 1 unit out at us, just like it went 1 unit that way, I think. Because its radius right here is 1. So it's going to go 1 unit into the board. Should we do a different axis? Those are the interesting ones. Those are the ones that get tough.
Just a line.
So I don't know if we'll do the actual integral for this one, but let's just set it up. That's the hard part.
Like, what if, okay, so like, what if the line was like, just x equals 5?
Yeah, just do that one.
Line,
You want to do
5.
5, Austin? Let's do
Well,
5.
because this is like, that's how it is on C on number 11, and I thought I was doing it right, but apparently not.
Yeah, I'm having
Is it
issues
5
with
on that one too?
It's
No,
4.
it's 4.
All right, let's do 5. Good choice. All right, so let's pretend we've got the same region, okay? The thing that's different is now it says revolve about x equals 5. You could do
Well,
revolve
see,
about
but
x equals negative something too.
And in this one, the line is touching it, so you don't have to do the washer method, but I still don't know.
We should be able to do it no matter what though. So I'm gonna get rid of this dashed line so it doesn't distract us, okay? Sometimes those can be distracting. So 5 is out here. 2, 3, 4, 5. So instead of revolving it this way and spinning it horizontally this way, we want to like spin it horizontally this way.
So in this case,
So I like to think of a picture, in my head at least, I don't know.
so
This
wouldn't
helps
the
you
big
guys,
be just 5?
Let's think, hold on. I like to draw this other piece over here at the other edge. How far is this out? What's this x
That's
value?
5. Well, it's 5 out.
It's
So it's 10
out.
Okay, well, I meant like another 5
yeah.
out.
Yeah, I know. That's what he meant, yeah. Mine doesn't look right, does it?
No.
Dang it. It should be at 10. Maybe right here? We're only getting a 2-dimensional cross section of this solid when we draw this, right? It's actually solid. It's a weird shape. So you've got like red that comes out at you, goes there, goes into the board, and behind the board it goes back and circles back out at us. It's not really huge, is it? So we shouldn't get a huge volume out of this, is what I'm trying to say. So let's see. How should we do this one?
Carefully.
All right. So we got to think about where we're revolving. So
0 to 10.
we're going to have the same like bounds to our region.
No. Yes.
I
So
think
you're
so.
still
Our
doing
rectangles still
Ys.
apply, right? We've still got rectangles that are in this region, and then we've got to do those separate ones up there. So I think we have to cut it the same way. You guys agree?
Yeah.
So we're still going to have to go from 0 to 1 of something, dy, plus 1 to 2 of something, dy. So now let's try to think about this first one. When we're in this region right here, how are we going to revolve that around here? What's the radius of the disk?
The whole thing is 5.
The radius, not diameter. The radius of that disk is 5.
Yeah.
Whatever. So we're just going to put 5 squared.
No,
and be done
it's
with
going to
that?
be the 5 minus.
It'll be 5 up to 1.
5. I'm talking this region. We're going to have a radius of 5.
Yeah.
But we got to cut out this big cylinder in the middle, don't we?
Yeah.
So it's 5 minus 4.
Minus 4. Okay, so we've kind of like a washer problem, isn't it? So it's like 5 squared. We're going to do all of that, and then separately over here we're going to come as 4 squared and take that out. Okay? Now, the thing I always got confused about this, is this the same thing as if you went like this for that part?
No, it is not. No, 25
Why?
minus 16 is not
Give me
the
reasons.
same as 1.
So you're giving me numerical reasons, right? We know that when you expand this out with FOIL or expansion techniques, it's not that, right? You have cross terms. So that's something you gotta be careful about. Sometimes I make mistakes on this if I'm not careful about that. Okay? Are we good? Can we go on to the next part?
Yeah.
Questions? Remember, it's because we're taking this big disk, making it entirely solid, and then cutting this disk out.
So
Okay.
the big disk is
But now
still
we've got to
the
do
same.
this region up here. The big disk is still,
5.
yeah. But now once we're up here, I think the ball game changes.
Is the biggest the biggest is going to be that equation?
So let's
here.
imagine, isn't the radius? See, I need another marker. I need another marker color. Mr. Parks, you wouldn't have one on you, would you?
No, I usually do, but I don't. I'll go get you a green one, but it'll be too late by the time I
Nah,
get
that's
back.
okay. No problem.
They only have
Um,
one pace.
Let's look at this. So, isn't that the big radius for this one right there? From here to here. Do you guys see how you need to draw these things in there? That's the big radius. So I'm going to call that big R for this part. Now the question is, how big is big R?
So is it
That
that equation?
is 5
It's
minus
y.
the y equation.
Isn't it just 5 minus this little part right here?
Mhm.
So it's 5 big R. Let's write it down separately. It's 5 minus. This is the hardest thing in this whole chapter right here. Is what we're doing. So we've got 5 minus. We need to take out this much.
Square root of.
But isn't this
5
much
minus
the
1.
x value of that curve? It's the x value of that curve. Did you have a green? Mr. Parks saves the day.
Well, I saw what colors you had.
I keep
I
forgetting.
that don't.
It's not a good
Yes. So we said it's 5 minus, and remember, the thing we're subtracting out is this region right here,
root
which is the
y
x
minus
value on this curve, which we did over here. Oh, we erased it.
You erased it. But it's root y minus
Square-
1.
Yeah.
So we had that a second ago. It was
Yeah.
y equals x squared plus 1. We solved, and we got x equals
Plus or minus.
plus
Yeah,
or
but you
minus,
only
but
need
we
the
want this
positive,
dimension.
Yeah, I know, but.
Okay.
It's minus 1.
That's why you spend all those hours.
Minus
learning
1, thank you.
versus- So you can do this problem later on.
This is like a cumulative math problem, isn't it, from like all experience you've had?
It's everything.
It is.
It's a culmination.
Okay, so are we okay with that? That's the radius that this is, so we're gonna put that as big R. We gotta do what with it?
Square it.
Yeah, so we gotta do, I should put some brackets in here.
This part's a lot harder than the first part, huh?
Yep.
At least the second part's the same.
Okay, now I think the second part, what's the little r for this? What do we wanna subtract out when we do that?
4.
It's still 4, isn't it? The part we don't want is this part. We're just wanting this little extra bit, this little red region that's been spun around up here. We don't want any of this blank stuff, so we gotta get rid of that. So again, little r here is gonna be 4 again. So I think the keys on this problem, and then I know you guys
You
can
still need
integrate
your
that.
pies, don't you?
Do I? Of course I do.
It's a circle, probably.
Thank you.
What's cool is that this part is still right in here, see it? Because when you expand this, you're gonna get 25. So you're gonna get 2 of these. Can you see 2 of those in there?
Let's see.
You guys know what he's talking about? Can you like expand that out? You're gonna have to expand that out. When you integrate this, what are you gonna have to do? expand it out, right?
25 minus 10y.
I'll let you guys do it. Go ahead and finish.
The thing is, here's the other one. See, this is 5 squared. When you expand this, you get your 25 minus your 16, which is the same as this.
Yep.
So you get 2 of those. In the picture, you can see it's right here. You see it? Remember this one? And then you have another one right there. So you got that double thing like this.
Oh, yeah.
So
That's
then
nice.
the rest of the junk that's in the middle here
Is what you're subtracting out.
Yeah.
That's the part that
Exactly.
that's going to be in there that's subtracted out. That's nice.
That's cool. Which means there's another way of doing that part, isn't
Yeah.
there?
Bye, Mr. Parks.
Sorry, I got in the way.
No, you're
It's
fine.
okay.
That was good. That's right. That's really cool.
I don't get it.
Okay, go, 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 go.
Go, go, go. Can't expand.
It's
Down.
going to take you a second.
No, it's not. It's gonna take me longer than a second. This is a lot.
This step, like the big R, little R thing.
It's not super easy. I'm taping this though, so you go back and watch it again if you need to.
Yeah.
As long as I get tape, I won't Sometimes I forget. It's not funny.
It's a little funny.
I've done it before. I get so mad.
How do you expand it? Oh, you haven't.
So this one, I'm gonna upload it. Like I was telling Brett, this is a good one. If you're getting stuck on yours, go back and look at this one. I think I explained it decently. So
50 minus, what's
I don't know.
20?
I'm gonna math night. So.
Oh,
I'm
come on.
Cheater. Cheater. 32.
Having from you and Caitlin. Holy sure.
Oh, that first one's easy. It's just 25 minus 16. That's 9. You go with 9.
Yeah. Oh.
No. 50 minus 32 is 18. Minus 20. What?
Oh, I didn't let me. I was like, I just hated her. Austin's not very nice about it either.
9, 8. Ooh, don't know.
That's what the calculator told me.
That's probably what I have. Give me a minute. 6.
No,
Minus.
This integral, if you're doing it, I'll just show you. The rest of it you guys should be able to do no problem. This integral is 25 minus 10 root y minus 1 plus y minus 1.
Oh my gosh, I got that part. I'm
So you get 25 minus 1 is 24 plus y. Those parts are easy. Minus 10 root y minus 1. You gotta do a u sub on that, right?
That's 67, not 71.
Oh, is there minus? I was just doing this there. But minus, let's do minus 16, put that in there too. So minus 16 and 24 is 8. Like that. And then this, you just do u subs, so this would be like 8. You should get 8y plus y squared over 2. Minus, pretend that's root u. So it'd be u to the 1/2. So that's u to the 3/2, 2/3 with a 10 out there.
So it's 21 minus 1 to the 3/2
U
over.
minus 1. 20 thirds. Okay?
Okay.
Anyway, that's what you get. So one more time, let's look at this, because this big R thing right here is what's hard, right? Let's look at it one more time, and then if you need to review the video, you can. So the first part, we said in this region right here, we've just got big radius is 5. We want to subtract out this big giant hole in the middle, which has a radius of 4. That part's not too bad. Then once you move up here, you've got to say the big radius is out to the edge right there, right? Or out to the edge right there, or whatever that is. But that's going to be the whole thing, which is 5, minus this little piece in here, which we're going to call, that was this little piece in here. I could even draw it in there. This little piece right here, from there to there, is x equals root y minus 1. Okay? And then we subtracted out 4 too. Okay? That can be a little tricky, I think, for sure. All right, you guys have the rest.